This program uses ideas introduced earlier, all of which are applications of similarity. For example, if you expand or contract this triangle, you change the lengths of its sides, but you don't change the angles or the ratios of corresponding sides. For any triangle, the perimeter is the sum of the lengths of its sides. If we expand or contract the triangle by a scaling factor, S, the perimeter is multiplied by the same factor. The same is true for perimeters of any two similar figures, even if they have curved boundaries. Expanding or contracting by a scaling factor multiplies the perimeter by the same factor. Let's apply this idea to a circle of diameter 1. Its perimeter, also called its circumference, is about 3.14. Scaling by a factor d gives us a similar circle whose diameter is d. And the circumference is multiplied by d. The ratio of circumference to diameter is the same for all circles, large or small. This constant ratio, which we'll see in another program, is denoted by the Greek letter pi. The circumference of a circle of diameter d is equal to pi times d. In terms of the radius, the circumference is 2 pi r. The history of human progress centers around the wheel. The wagon wheel removed the load from man's back and made him better than a beast of burden. The wheel brings water to crops, turns wheat into flour, converts nature's energy into electricity, and transports people and goods to the ends of the earth. Circular motion is present in machines that have dominated our way of life, from ancient times to modern times. To relate circular motion to mathematics, look at this circle of radius 1, called a unit circle. The length of its boundary is 2 pi. When an object moves along the circumference, the distance it travels can be recorded on a horizontal t-axis. The number t is called the radian measure of this angle. The word radian is short for radial angle. When you wrap one radius of a circle along its circumference, the angle formed is 1 radian. If you want to fill the entire circumference, you need a little more than 6 radians, 2 pi radians to be exact. This angle, halfway around the circle, is called a straight angle and contains pi radians. This one, 1/4 of the way around, is called a right angle and contains pi over 2 radians. And half of that is pi over 4 radians. When a bright spot moves around a circle, what you actually see depends on your point of view. You see a true circle only if you look at it from the right direction. You might see motion along an oval curve called an ellipse. Or you might perceive the motion as being straight up and down, as though the spot was casting a shadow. The height of the shadow above or below the shadow of the axle can be measured on a vertical y-axis. When you plot y against the angle t, you get a graph called a sine curve. The number y is called the sine of t, and written this way: y equals sine t. The word sine is the English form of the Latin word sinus, which means bend or curve. In this program, we will become better acquainted with some sinuous curves. Now let's look more closely at the sine curve. The sine of 0 is 0. As the angle increases from 0 to a right angle, the sine increases from 0 to 1. As the angle continues to increase from a right angle to a straight angle, the sine curve drops back to 0, forming a symmetric arch. The arch is symmetric about this line because the circle is symmetric about this diameter. If this is t, this is pi minus t. So the symmetry of the arch can be written as a simple equation. The sine of pi minus t is equal to the sine of t. The two angles, t and pi minus t, are called supplementary. The sine of an angle is equal to the sine of its supplement. Let's continue examining the sine curve. As the angle increases from pi to 3/2 pi, the sine is negative, and it stays negative until the angle reaches 2 pi. Look at its graph from pi to 2 pi. If you slide it back pi radians, it's just the first arch flipped over. And here's why. If this is t, this is pi plus t. The sine of pi plus t is the negative of sine t. As the point moves counterclockwise around the circle several times, the basic shape is repeated over and over. Any curve obtained by repeating one shape indefinitely is called periodic. If the point moves around the circle in the opposite or clockwise direction, the angle swept out is considered negative. Here's the sine curve plotted along the negative t-axis. The circle is also symmetric with respect to this diameter. If this is t, this is negative t. The sine of negative t is the negative of sine t. This is another axis of symmetry for the circle. But when we reflect the sine curve through this line, we get a new curve. Let's look at this curve. If this angle is t, this one is pi over 2 minus t. The two angles, t and pi over 2 minus t, are called complementary. The sine of the complement of t lies on our new curve. It is called the complementary sine, or cosine, and it's written like this. The cosine comes from flipping the sign about the pi over 4 line. So, on the circle, the cosine is the horizontal x-coordinate of the point, just like the sine was its vertical y-coordinate. In other words, when a point moves on a unit circle through an angle of t radians, its rectangular coordinates are x equals the cosine of t and y equals sine t. Here's another way to get the cosine curve. Start with the sine curve and shift it to the left by pi over 2 radians. If this is t, this is pi over 2 plus t. The cosine of t is also equal to the sine of pi over 2 plus t. So we have two ways to relate the cosine and sine. Cosine t is the sine of pi over 2 plus t, and cosine t is the sine of pi over 2 minus t. Sine waves also show up in phenomena that have nothing to do with circles. For example, a vibrating tuning fork sets the air next to it in motion, alternately compressing and expanding it with each vibration. The variation of sound pressure can be detected not just with your ear, but also with a microphone connected to an oscilloscope that traces out a sine wave, showing how the sound pressure varies with time. We can also make sine waves with an electronic synthesizer. The number of vibrations per second is called the frequency. It's related to the sound or tone. For example, this tone has a frequency of 440 vibrations per second. Here's what happens if you double the frequency. The new sound, an octave higher, is called an overtone. And here's what it sounds like if you cut the frequency in half. The new sound is an octave lower. The height of the curve, up or down, depends on the loudness or intensity of the sound. The maximum height of the curve above the axis is called its amplitude. These examples show changes in amplitude for a given frequency. More complex sounds can be made by combining sine waves. For example, if you combine this tone with this overtone, the graph of the combination is obtained by adding the corresponding heights of the two sine curves. It sounds like this. instruments make more complex waves. Here's the same note played on many different instruments. The same note has a different quality on different instruments because each produces a different combination of overtones and amplitudes. And of course, if you play many notes on many instruments, the graphs get much more complicated. The sine curve is periodic because it consists of a basic shape repeated indefinitely. Here are some other examples of periodic waves. A square wave, a sawtooth wave, and there are many more. In fact, you can draw any graph that returns to its original value in an interval and repeat the graph indefinitely to obtain a periodic wave. In the early 19th century, the French mathematician Joseph Fourier, who was also a public administrator appointed by Napoleon Bonaparte, astounded the mathematical world when he announced that every periodic wave is a combination of sine and cosine waves with appropriate amplitudes and frequencies. For example, here's how sine waves combine to approximate a square wave. To any degree of accuracy. This example reveals an interesting phenomenon. Watch the two highest peaks on the sine wave approximation. As we use more sine waves, these peaks move away from the center but remain above the square wave by about 16%. This is called the Gibbs phenomenon, in honor of Yale physicist Josiah Willard Gibbs. This sawtooth wave can be approximated by cosine waves. And this one, made by a trombone, is a combination of both sines and cosines. Ancient manuscripts tell us that sines and cosines originated in early astronomy. Because planets were thought to move in circular orbits, astronomers were interested in chords of circles. This Babylonian clay tablet contains a list of chord lengths used for astronomical data. The Greek mathematician Hipparchus, the father of trigonometry, wrote a treatise on chords of circles around 150 BC. Some 300 years later, Ptolemy of Alexandria produced the Almagest, a remarkable collection of 13 books on mathematical astronomy. One chapter consists of a table of chords of circles. Today, this would be called a table of sines. In trigonometry, the study of triangles, sines and cosines appear as ratios of numbers. Look at this right triangle. Suppose we call this angle t. If we expand or contract the triangle by a scaling factor, we change the length of the sides, but we don't change the angle t or the two internal ratios, a over c or B over C. Now we will show that the ratio A over C is equal to the sine of t, and the ratio B over C is the cosine of t. Scale a triangle by the particular scaling factor 1 over c. This gives a triangle with a hypotenuse of length 1. Use this as the radius of a unit circle. Then t is the radian measure of this angle. This point has a vertical coordinate, sine t, and a horizontal coordinate, cosine t. But these are just the lengths of the other two sides of the triangle. This shows that sines and cosines are ratios of lengths of sides of a right triangle. If the right triangle is oriented differently, it's easy to remember the ratios by thinking of them this way. The sine of this angle is the length of the side opposite the angle divided by the length of the hypotenuse. And the cosine of the angle is the length of the side adjacent to the angle divided by the length of the hypotenuse. These ratios were used in early trigonometry and astronomy and are still used today in large-scale construction and in navigation. Not only from Los Angeles to Hawaii, but also from planet Earth to planet Mars. In fact, cosines occur in formulas for describing the elliptical motion of a planet or a spacecraft moving around the sun. In this program, we've seen how sines and cosines appear in different ways. As the rectangular coordinates of a point moving on a unit circle, as graphs related to vibrating motion, and as ratios of lengths of sides of right triangles. Hipparchus is considered the father of trigonometry because of his books on chords of circles. These books are now lost, but many of the ideas have survived in Ptolemy's Almagest, the oldest existing work on astronomy. This program has revealed only a small sample of the interesting properties of sines and cosines. In the next program, we'll explore new properties. For example, we'll learn about the law of cosines, which relates the lengths of the sides of any triangle. We'll also learn about the law of sines, which says that in any triangle, the ratio of the length of a side to the sine of the opposite angle is constant. And we'll discuss addition formulas that tell us how to find the sine and cosine of the sum of any two angles. From these, we'll learn that if you combine a sine wave with a cosine wave of the same frequency, you just get another sine wave, possibly shifting. And we'll learn how to calculate sines and cosines to any desired degree of accuracy, the way it's done in your pocket calculator. Sines and cosines play a fundamental role in analyzing oscillating systems. A marble rolling in the bottom of a bowl, a mass oscillating at the end of a spring, water waves, alternating currents, radio waves, and the wave theory of light. In fact, everything we see or hear reaches us through wave motion that can be analyzed with sines and cosines. The mathematics of sines and cosines helps us better understand the world around us.